Alright everyone, I know you're excited to get back to factoring and solving trigonometric equations. So we're doing day 3 of section 5.3, solving trig equations. This time we're going to have trig equations where there are more than one type of trig function in them. For example, in our first problem, 2 times cosine squared of x minus sine x minus 1 equals 0. Cosine and sine are not compatible. We can't combine these types of terms. We can't even factor them because they're not alike. Fortunately, we know our identities from chapter 5, section 1, and so we can change cosine squared or any squared function into another one. And luckily, cosine squared actually changes into sine squared. So I'm going to go ahead and write my identity now. The Pythagorean identity says that sine squared plus cosine squared equals 1. So I can solve for cosine squared by subtracting the sine squared over. And so we get cosine squared of x equals 1 minus sine squared x. And I want to make sure I put that in a grouping symbol. To remember, these have to stay grouped together if I'm going to replace them with cosine squared. So here's my replacement. 1 minus sine squared x. I'm going to replace that with the cosine squared x right here. And that parentheses will help me remember that I need to distribute the 2 when I do the replacement. So right here now, I'm going to write 2 times parentheses 1 minus sine squared x minus sine of x minus 1 is equal to 0. And now this is just like the problems that we were doing in the previous lesson in 5.3.2. We have a squared sign and a regular sign, and so we're going to have to try to factor this at some point. But there's a lot of simplification I need to do before then, so let's go ahead and simplify this. I'm going to distribute the 2 to make this 2 minus 2 sine squared x minus the single x minus 1. Okay, we can't combine the sine squared x and the sine x, but if I could get this into a trinomial form, hopefully I can factor this. So let's see, 2 with the negative 1 is going to combine to be 1. So I'm left with negative 2 sine squared x minus sine x plus 1 is equal to 0. So I just combine those two like terms. And there's my trinomial. Unfortunately, I don't really like that I lead with a negative, so I'm going to multiply everything by a negative sign. So if I multiply the entire expression by a negative 1, as long as I do it to both sides, it should still be true. This is 2 sine squared x. This is going to change to a plus sine x. And this is going to change to a minus 1. Okay, and now this is a good factorable trinomial, one that we're used to. This is like 2x squared plus x minus 1. So if you want to imagine that sine x is going to be the same thing as our x now, we can rewrite this as 2x squared plus x minus 1 equals 0. And this might be easier for some of you to try and factor with, and then just replace x with sine x once you're done. So let's see, if I try to factor this, I know I need to lead with a 2x and a x. And we want it to be a positive 1, so I'm going to need a positive 2 in the middle, and then subtract 1 from that. So we get 2x minus 1 times x plus 1. You can FOIL that and see that, yep, it will be 2x squared plus 2x minus x minus 1. So that will be equivalent. And now we can go back and change all of our x's back to sine x's. So really this is 2 sine x minus 1 times sine x plus 1. And for some of you this step might not be necessary. You might be able to factor just as easily with sine x as you can with x. Each person is a little bit different in what they prefer. So now that I have it factored, I'm going to use the zero product property by setting each of the factors equal to 0. Remember, this is like your a times b equals 0. That means either a is 0 or b is 0. So I'm going to have two separate equations now. The first one is 2 sine x minus 1 equals 0. When we solve for sine of x here, we got to add the 1 over and divide the 2. I'm going to do that one step. So I'm looking for solutions where sine of x is equal to 1/2. We'll solve that in a second. And I'm trying to solve for when sine of x plus 1 is equal to 0, or when sine of x is equal to negative 1. So we'll take out the unit circle, which I have stored right here. Let's take a look at that. Alright, let's see, sine of x is 1/2. That'll occur at pi over 6. So I have the solution at pi over 6. And they did tell us this time to use the interval from 0 to 2 pi, so we're going to make sure we use the entire interval. Find any time that it's equal to 1/2. It's going to equal 1/2 again at 5 pi over 6. And then we're also looking for when sine of x is equal to -1. That's going to be at 3 pi over 2. Okay, so we have 3 solutions for this problem. Okay. All right, try this one on your own. This one doesn't have it set equal to 0, so I'm going to add the cosine x and subtract the 1 over at the same time. So now it's set equal to 0, which I like. This is 0 equals 2 sine squared x plus cosine x minus 1. And now we can do our replacement like we did before. We don't want to have a sine squared and a cosine. We want them to be the same trig function. So remember, sine squared of x is equal to 1 minus cosine squared x. So that's what I'm going to plug in here. This is 2 times 1 minus cosine squared x plus cosine x minus 1. So we'll go ahead and distribute 2 minus 2 cosine squared x plus cosine x minus 1. You get that pesky negative out front again. This is negative cosine squared x plus cosine x plus 1. Very similar to what we just factored. I'm going to multiply by the negative and get 2 cosine squared x minus cosine x minus 1. And then we factor that, we get that this is 2 cosine x plus 1 times cosine of x minus 1. I'm going to double check my work there because I kind of did it in my head. See, 2 cosine x times cosine x is 2 cosine squared x. 2 cosine x, that's minus 1. Or sorry, it's minus 2 cosine x is plus 1. That's good. Minus 1. Okay, so it checks out. And now we're going to set each of these using our zero product property equal to 0. So 2 cosine x plus 1 equals 0. And cosine x minus 1 equals 0. So when we solve for cosine of x, we get cosine of x is equal to negative 1/2, or cosine of x equals 1. Let's see, I'm going to need to go back and get my unit circle. There's that right here. Alright, so we're looking where cosine of x is equal to negative 1/2. So that's my x coordinate. Only looking for the negative 1/2, again, all the way through the unit circle. Negative 1/2, that occurs right here at 2 pi over 3. Negative 1/2 also occurs down here at 4 pi over 3. And the cosine of x is 1. Cosine of x is 1 right here at 0. So notice they put a parenthesis around 2 pi. They don't want us to use 2 pi. They want us to use 0 instead. They put a bracket there. So we're going to say it also has a solution at 0. Okay. So all we know, 0 and 2 pi are the same thing. 2 pi is not allowed to be in our interval, so don't use that one as your solution. Okay. I'll move that off to the side here. Alright, we have one other example to work on today. And that's sometimes you can solve these equations by squaring one of the sides. We're going to find all solutions of cosecant x minus cotangent x when it's equal to 1. So we're going to go ahead and try to solve this by squaring both sides of the equation. This technique can be used if you notice that you don't have anything that's squared that you can use Pythagorean identities to replace. So we know that cosecant and cotangent are in a Pythagorean identity together, but since in this equation neither of them are squared, we're going to try to square both sides of the equation to force them to be squared. General warning on these do create extraneous solutions when you do that. So we might have to check and see if our solutions actually work when we're done. Okay, so cosecant of x minus cotangent of x is equal to 1. I don't want to have to square both of these together. I just want to move the cotangent of x over to the other side. And so I get the cosecant of x equals 1 plus the cotangent of x. And this will be easier for me to square both sides with, because then I'll just have cosecant squared. If I squared this big binomial on this side, it would create a lot of different terms that I won't like. So always try to put each of the two different trig functions on different sides of the equation before you square both sides. So I'm going to make sure that I square the entire side of each of the equation. The left side just becomes a simple cosecant squared x. On the right side, I need to square this binomial. So you can either distribute or FOIL it, or if you just know how to square a binomial, this is 1 squared plus 2 times 1 times cotangent plus cotangent squared. Okay. Whichever method you're most comfortable with squaring a binomial, you should get this when you finish simplifying it. So now we have a cotangent x and a cotangent squared and a cosecant squared. And I know that I can change cosecant squared using my Pythagorean identity. So I'm going to say, okay, cosecant squared x is equal to 1 plus cotangent squared x. That's one of my Pythagorean identities. So I'm going to do a replacement here. This is just going to change to 1 plus cotangent squared x. And I have 1 plus 2 cotangent x plus cotangent squared x. And now it looks like there's a lot of things that I can actually cancel out, which is very nice. I can subtract the 1, those will cancel. And I can subtract the cotangent squared x, those will cancel from both sides. So on one side of my equation, I'm just left with a 0, and on the other side I have 2 times cotangent of x. So when we divide the 2 over and try to solve for cotangent, we're looking for when cotangent of x is equal to 0. So let me go back and get my unit circle. I got it right here. Okay. Now, if the cotangent of x is 0, that means the tangent of x should be undefined. Remember, we take the reciprocal 1 over 0 is called undefined. And so if we look on our unit circle when tangent is undefined, between 0 and 2 pi, we get that it is undefined at x equals pi over 2 and 3 pi over 2. And we'd be done at this point, except that remember we talked about how we can create extraneous solutions. So we want to plug these back into the original equation and see which ones actually work. So we need to take the cosecant of pi over 2 and subtract the cotangent of pi over 2 and see if that gives us 1. So if I take the cosecant of pi over 2, I really want to take the reciprocal of sine. So I'm going to take the 1 over sine of pi over 2. And this is the reciprocal of tangent, so this is really 1 over tangent of pi over 2. So let's see here, 1 over sine of pi over 2. Sine of pi over 2 is 1, so this is 1 over 1. Minus 1 over, this was undefined, right? The cotangent of pi over 2 we said was 0. So 1 over undefined is really equal to 0. So we get 1 minus 0 equals 1. That one checks out. So now we just need to check our other one. If we try the cosecant of 3 pi over 2 minus the cotangent of 3 pi over 2, seeing if that equals 1. The cosecant of 3 pi over 2, sine would be negative 1. The reciprocal of negative 1 is negative 1. Minus the cotangent of 3 pi over 2, it's still undefined, so we still get 0 when we take the reciprocal of it. We get negative 1. That is not a solution. So we need to cancel out 3 pi over 2. It doesn't work. The only solution is pi over 2. Okay. For your final problem, try this one on your own. I'll post the work in just 1 second. Go ahead and hit pause now. Try it on your own. Okay, so there's the work for the final problem. I'm not sure why, but I decided to subtract 1 over and square it at that point. You could have squared it right away. There's no reason why you'd have to have negative 1 with tangent. So if you did it the other way, that's fine. They had already separated secant and tangent on opposite sides, so it's pretty much ready to square both sides. Once you square both sides and do the replacement with the Pythagorean identity, then you should get that 0 is equal to negative 2 tangent x. And when you find out when tangent is equal to 0, it's at 0 in pi. Fortunately, 0 does not work when I plugged it back in up here, but pi does work, so pi is our only solution. Okay. That's it for today. Hope you guys have a great afternoon.